Hello, my name is Laura Crosilla and I'm a researcher at the University of Oslo. This video is on the infinite and paradoxes. Infinity in mathematics is the topic of my research grant sponsored by the Horizon 2020 program of the European Union. In this video, I'm helped by Jamel, who will be introducing next to the infinite.
The most beautiful idea in mathematics is that of the infinite. The infinite never stops. It goes on forever and ever and ever again. Thinking of the infinite makes our head spin.
The infinite.
What is the biggest number you can think of? Can you think of a number even bigger than that? And another one? What is going to stop us thinking of bigger and bigger numbers? The infinite is written with this symbol. That means we can go on and on and on around it.
How many thoughts can you think of?
Think of something like the number 1. Now think of this thought. Again, think of this new thought, and so on. Now think of all your thoughts. This is a new thought. Can you think of one more thought, and then another one, and so on?
Inexhaustibility.
The infinite is inexhaustible. No matter how far we reach, we can always add more. Think of the numbers 1, 2, 3, 4, 5, and so on. Or 0, 1, minus 1, 2, minus 2, 3, minus 3, etc. There is no bound or limit to how far the numbers go on.
The infinite and our finitude.
The infinite is inexhaustible and enormous, but we are finite and small. This is a picture of us, finite and small, compared to the infinite, inexhaustible and enormous.
Paradoxes.
What do you think is a paradox? A paradox is a sentence that forces us to reach false or even crazy conclusions. Example, the liar. Suppose I say, I'm a liar. If I am a liar, then all what I say is false. But then also the sentence, I'm a liar, is false. This means that I am not a liar and I said something true. So am I a liar or not?
Paradoxes of the infinite. Number 1.
Achilles and the tortoise. Achilles and the tortoise compete in a race. The tortoise is given a good head start over the speedy Achilles. Soon after the race starts, Achilles reaches the tortoise's starting point. By that time, the tortoise has advanced a bit more. By the time Achilles reaches this new point, the tortoise has advanced a little bit further, and so on.
Okay, now we can see this in a video. Like if we were looking from above, we have Achilles' starting point and the tortoise. When Achilles reaches the tortoise, by that point, by that time, the tortoise has gone a little bit further ahead. But then Achilles will quickly reach the new point where the tortoise was. By that time, the tortoise has also gone a little bit further ahead. Or we won't take very long to Achilles to reach a new point. But by that time, the tortoise will have moved a little bit more forward, and so on. So Achilles will seem that he will never reach the tortoise at all. Let's now look at another paradox of the infinite, the second paradox of the infinite, Hilbert's hotel.
Imagine a hotel with infinitely many rooms, all occupied. When a new guest arrives, the guest in the first room moves into the second room. The guest in the second room moves into the third room, and so on, making room for the new guest.
So it looks like there's always place for as many guests as you want. Paradoxes of the infinite, number 3.
Galileo's paradox.
Let's remind us of what the whole and the square numbers are in preparation for Galileo's paradox.
The whole numbers are 1, 2, 3, 4, 5. How many whole numbers are there? The square numbers are 1, 4, 9, 16, 25. How many square numbers are there? Are there more whole numbers or square numbers?
So let's try and see. Let's write them down. Let's write 1, 2, 3, 4, 5, and so on. And in the next row, we write down 1, the first square number, and then we write nothing because 2 is not a square number, 3 is not a square number. However, 4 is a square number, yes, we write it down. 5 is not a square number, and so on. So if you write it in this way, it will look like there are more whole numbers than squares. We have apparently from this picture more numbers on the first row than in the second one. But let's look at things from a different perspective. Let's write down everything again now in a different way. So we write down 1, 2, 3, 4, 5, and so on, as we did before. But now let's write down the square numbers in a clever way. So we write under 1, we write 1, which is its square, and then under 2, we write the second square number, 4. Under 3, we write the third square number, which is 9. Under 4, 16, which is the fourth square number, and under 5, 25. So it looks like we can pair up the whole numbers with the square numbers. 1 is in the pair with 1, 2 with 4, 3 with its square 9, 4 with its square 16, and 5, 25. This means that if we look at this from this perspective, it will look like if there are as many squares as whole numbers, contrary to what we thought before.
Galileo thought that the whole numbers and the squares are infinite, and that for that reason the usual words equal, greater, and less cannot be used in their case. These words only make sense when talking of small, finite quantities.
So Galileo wrote about this in his Discorsi e dimostrazioni matematiche intorno a due nuove scienze.
1638. These paradoxes highlight our struggle to make sense of the infinite.
We are small and little, finite and bounded, and we look at the infinite, which is enormous, inexhaustible, and unlimited.
The infinite. A question. Which of these three paradoxes did you like the most? Can you think of another paradox of the infinite? What did you find the most surprising in this video? What else would you like to know about the infinite?
To find more about my research, see my webpage. And I'd like to say thank you to Jamel for reading this text and helping me design these slides. And last of all, thank you very much for listening. Thank you so much. Bye-bye.
Bye.